This video is going to cover reactions at the benzylic position as well as some reactions at benzene itself. First, what is the benzylic position? It is any of the three positions that are connected directly to the aromatic ring. The reactions that we'll cover include free radical bromination, substitution, elimination, and oxidation. You already know the substitution and elimination reaction, so we're only learning two new reactions here. The first is free radical bromination. Here we can do this with the molecule NBS with heat or light. NBS is shown over here and it's a source of bromine. Or we can use elemental bromine and light. We're going to review the mechanism for the bromination with elemental bromine. Elemental bromine is in an equilibrium with the bromine radical, and whenever the bromine radical is present, it can abstract a hydrogen atom from this benzylic position to form a radical intermediate. Then that radical intermediate can react with elemental bromine to form an alkyl or benzylic halide. Oh, it's missing its aromatic ring there. Let's give that back. It also creates an equivalent of the bromine radical, and that bromine radical can either go on to further abstract hydrogen atoms from other molecules in the reaction, or it can recombine with another radical of bromine to form elemental bromine. You can skip the NBS mechanism until we get to chapter 10, but you need to know this reagent and what it does. Substitution reactions are what we've already covered before. You know that with a primary alkyl halide, or in this case benzylic halide, that reaction with a strong nucleophile results in an SN2 reaction. So here we have sodium methoxide replacing bromine as a good leaving group to form this ether. In the second case, we know that if you have a tertiary alkyl halide and treat it with water, then we can get an SN1 reaction to form an alcohol. In elimination reactions, you know that if you have a strong bulky base, a good leaving group, and a beta proton, then you can undergo an E2 reaction. And in the last example, when you have a tertiary alcohol, you can use concentrated sulfuric acid and heat to undergo a dehydration reaction in an E1 mechanism. Next, we'll discuss the oxidation reactions. When we treat benzene with an oxidizing agent such as sodium dichromate, no reaction occurs. The same thing happens when we have alkyl groups. No reaction occurs. But once we have primary and secondary benzylic positions, this is oxidized by sodium dichromate to form the carboxylic acid. In the case of the tertiary substituted benzene, we do not get a reaction in this case. This reaction also works with potassium permanganate. We know those oxidation conditions from our chapter on alcohols. So this is a really handy way to transform an alkyl group with no reactivity, with no functional handles, to something that has reactivity. We can also reduce benzene and its derivatives, and that's what we'll focus on in section 17.7. The first way that we'll reduce benzene is with a hydrogenation. We know that with hydrogen on palladium, no reaction on benzene occurs, but if we have an alkene that's not part of the aromatic ring, it gets reduced. To reduce benzene to cyclohexane, we need to use a stronger reducing agent, so we're going to use hydrogen with nickel at 100 atmospheres and at 150 degrees, and that gives us cyclohexane. Those conditions are also, of course, reactive enough to reduce an alkene that's not part of an aromatic ring. You don't need to know the mechanism for this reaction, but certainly know the reagents. The next reaction we're going to cover is the Birch reduction, and in this reaction we're reducing benzene using sodium in the solvent methanol and in the solvent liquid ammonia to get cyclohexadiene. In this mechanism, we have a reduction of the benzene ring. So that we get a radical anion, and then this is protonated by methanol at the anion position, giving us a neutral radical. This radical is further reduced to yield another anion, and that is protonated by methanol to give us cyclohexadiene. In this reaction, we observe different outcomes depending on whether the benzene group has an alkyl group or an electron withdrawing group. Why do we get these different outcomes? The answer comes in looking at the stability of the intermediates. When you reduce benzene derivatives with sodium, you have the choice of having a radical anion where the anion is close to the R group, or where it is one carbon over from the R group at the ortho position. When we have an R group, we know that that's electron donating, so we want our anions to be further away from it. So that means that this intermediate is more stable, and it's going to be what leads to the product. With an electron withdrawing group, though, that situation is different. Instead, the intermediate that has the anion closer to the substituent is more stable because the substituent is electron withdrawing and takes those electrons in through resonance. So here's some practice. Predict the products of the following Birch reductions. I'll let you put your video on pause and work through these two reactions. In the first case, what we want to do is reduce this aromatic ring with sodium and form a radical anion. And we want this radical anion to have to be in conjugation with the carboxylic acid, giving us this intermediate. And that is going to lead us to, after a few mechanistic steps, to this product. In the second case, we have symmetry, so it's not going to matter whether we have the alkenes going one way or another, because the product is going to be symmetrical whether we form this or this. They're both the same. So in this case, the position of the alkyl groups don't matter. Let's do some more practice. Let's wind up this lecture with some more practice. So I want you to develop a multi-step synthesis to accomplish the following transformations. So I'll let you put your video on pause and work on both of these transformations. And when you unpause it, we'll solve both of them. In the first example, we can see that the number of carbons is the same, and we want to form an alkene. So we're thinking about, because we don't have any tertiary carbons, we want to undergo an E2 reaction at some point to get to this alkene. So how do we go about that? We need to install a good leaving group so we can use a strong base for an E2 reaction. And the way we're going to do that is install a bromine atom at the benzylic position, and we know that we can do that with NBS and heat, NBS and light, or bromine and light. In the second example, we want to form an ester, and that makes me think of forming a carboxylic acid. We know that with a with having an ethyl group on this benzene, that we can use potassium permanganate to form this carboxylic acid, or we could have used sodium dichromate as well. And then to convert that to an ester, we want to use a base. We can use sodium hydroxide here because the pKa of that carboxylic acid is about 5. So sodium hydroxide is a strong enough base to deprotonate that. And then we want bromomethane as our electrophile. I actually gave you the... Let's pause your video to work through these two examples. Now, in the first case, wrong molecule here, so that was the same as before. What I meant to give you was this one. So if you start over again with that molecule, sorry about that. What stands out to me in this reaction is that we have the incorporation of a new carbon atom. So we know at some point we're going to have to be using a Grignard reagent. And that means that we need to have a ketone or another carbonyl so we can attack that carbonyl position. Now, the only way that we know how to install a carbonyl here is to use our oxidizing agents to form a carboxylic acid. But note what that's made us do. We've lost this carbon atom, this methyl group. So that means we're going to need to install 2 methyl groups again to get to our product, which has 2 methyl groups here. We know that if we add a Grignard reagent to an ester 2 times, that we'll get the addition of those 2 Grignard alkyl groups. So that's what we're going to need to do next, is to form an ester. It doesn't matter what ester we form, but let's just form a methyl ester. Then when we treat this with an excess of, go ahead and change that to the Grignard reagent itself. This gives us our alcohol with 2 new carbons. So these are the 2 new carbons that we installed with this methyl group. And to be thorough, let's put an excess of the Grignard reagent. And then to get to our product, we just need concentrated sulfuric acid to cause an E1 reaction to occur. And in the second example, this was supposed to be an E after that methyl group. So because of that error, let me have you pause your video again and work on that problem. And then we'll see how to solve that. So this is a shorter problem. We basically need to have something with a leaving group to be able to undergo a substitution reaction. Notice that this, because the carbon is secondary, this is going to be low yielding, and the major product will be this. But if we want to get to this ether group, this is the only way we can go about it. So again, we're going to use NBS and light, or bromine and light, to get there. That I have for you today, we'll pick up on NMR spectroscopy in the next lecture. And that is all